morning to all of you. So in this semester, I am going to teach you digital image processing. So there is a no good book. So there are a number of books from which I had taken some pictures and concept. And the most popular book in this field is Digital Image Processing by Gonzalez and Woods. The other book is Fundamentals of Digital Image Processing by Anil K. Jain. So there are a number of other references books, you can go through that. So this course needs some basic concept of signals and system, and some basic concepts of algebra. And to perform a programming, you have some background of MATLAB. The course has been distributed as the lab will consist 20% of the marks, mid-semester 25%. There are 2 quizzes, so that will consist 20% of the total marks, and end sem is 35%. These are the course learning outcomes. So exhibit and knowledge of fundamentals of digital image and its processing. Exhibit the knowledge of image enhancement techniques in spatial and frequency domain. Elucidate the mathematical modeling of image restoration and compression. Apply the concept of image segmentation. Exhibit the knowledge of object detection and recognition techniques. So first, for a digital image processing, first we have to understand signals concept. So signal processing is a discipline in electrical engineering and in mathematics that deals with analysis and processing of analog and digital signals, and deals with storing, filtering, and other operations on signals. These signals include transmission signals, sound or voice signals, image signals, and other signals, etc. Out of all these signals, the field that deals with the type of signals for which the input is an image and output is also an image is in image processing. So in image processing, the input is an image and output is also an image. As its name suggests, it deals with the processing of images. It can be further divided into analog image processing and digital image processing. So what is analog image processing? Analog image processing is done on analog signals. It includes processing on a 2D analog signals. In this type of processing, the images are manipulated by electrical means by varying the electrical signal. The common example is television image. So television image is an analog image. And digital image, the digital image processing deals with developing a digital system that performs operation on a digital image. So what is an image? An image is nothing more than a two-dimensional signal. It is defined by a mathematical function f of x comma y, where x and y are the two coordinates horizontally and vertically. The value of f of x comma y at any point gives the pixel value at that point of an image, where x and y are the spatial coordinates, and at that coordinate the value of the image is known as intensity value. So this is a two-dimensional image, and that one is corresponding two-dimensional matrix. So here x and y axis are representing spatial coordinates, or you can see here we are taking a variable u and v, and corresponding u and v, the function value is an intensity value. So these are intensity value at different locations. So relationship between a digital image and a signal. If the image is a two-dimensional array, then what does it have to do with the signal? In order to understand, we need to first understand what is signal. So signal in physical word, any quantity measurable through a time over space or any higher dimension can be taken as a signal. A signal is a mathematical function and it conveys some information. For example, if signal does not have any information, then it is known as noise. A signal can be one-dimensional or two-dimensional or higher dimensional. One-dimensional signal is a signal that measured over time, and the most common example is a voice signal. So here you can see that it varies with respect to time, and the two-dimensional signals are those that are measured over some other physical quantities. For example, you can take a space. So the example of two-dimensional signal is a digital signal. So that varies, the signal varies in space. Since anything that conveys information or broadcasts a message in a physical world between the two observers is a signal. That includes a speech or human voice or an image. Since when we speak, our voice is converted to a sound wave or signal and transformed with respect to the time to the person we are speaking to. Not only this, but the way digital camera works, as while acquiring an image from a digital camera involves transfer of a signal from one part of the system to the other. So how digital image is formed? Since capturing an image from a camera is a physical process, the sunlight is used as source of energy or source of illumination. A sensor array is used for the acquisition of the images. So when the sunlight falls upon the object, the amount of the light reflected by the object is sensed by the sensor, and a continuous voltage signal is generated by the amount of sensed data. In order to create a digital image, we need to convert this data into a digital form. So this involves sampling and quantization. The result of sampling and quantization is a 2D array or matrix of a number which are nothing but a digital image. So in the later on slides, we are going to explain why we need a sampling and why we need a quantization. So there is an overlapping field between digital image processing and computer vision or machine vision. Machine vision or computer vision deals with developing a system in which the input is an image and output is some information. For example, if there are n number of students and we are going to train a system that will recognize those students from their facial recognition. So that is a part of computer vision. While if you are going to improve the quality of image, for example, there is a blur image and then you are going to perform some kind of processing and the output is a improved version of input image. So that is known, that comes under digital image processing. There is another overlapping field which is known as computer graphics. In computer graphics deals with formation of images from the object model rather than the image is captured by some device. For example, if there is a rendering of object that generated an image from an object model, such a system would look something like this. We have some object model and that generates a rendering of an object. So this system, this concept comes under computer graphics. Now what is signal processing? Signal processing is an umbrella and image processing lies under it. So you can say that image is nothing but a two-dimensional signal. So it comes under signal processing. So all those concepts which comes under signal processing that can also be implemented on images. So the amount of light reflected by an object is the physical world. In the physical world is a three-dimensional signal. And the three-dimensional signal is passed through the lens of the camera and it becomes two-dimensional signal. Hence the result is an image formation. So when the three-dimensional signal is passed through the lens, so three-dimensional signal is projected into a two-dimension. So that becomes an image. This image is then digitized using a method of signal processing, and this digital image is manipulated in digital image processing. So later on you are going to understand why we digitize those images. Now, to understand why we need a digitization, first we have to understand what is analog signal. A signal could be an analog quantity, that means it is defined with respect to the time. It is a continuous signal, means it defined at every point of time. These signals are defined over a continuous independent variable. They are difficult to analyze as they carry a huge number of values. So you can say that in between the time 0 to t, if the signal is defined, then there are infinite number of values between the 2 points 0 and t. In order to store these signals, you need a infinite memory because it can achieve infinite values on a real time. Analog signals are denoted by a sine wave. Example, human voice is an example of analog signal. When you speak, the voice that is produced travel through air in the form of pressure waves and thus belongs to a mathematical function having independent variable of space and time and value corresponding to a air pressure. So the output, on the output, on the y-axis there is a pressure, on the x-axis there might be a time or space. Another example is a sine wave, which is shown in the figure, where on the y-axis y is equal to sine of x and x is an independent quantity. Another example is of sine waves, which is shown in the figure below, where y is equal to sine x and x is an independent quantity. So this is an example of analog signal which is defined at every point of time. So you will get an infinite number of values in between 0 to t. So there is an infinite value on the y-axis also. Digital signal, as compared to analog signal, digital signals are very easy to analyze. They are discontinuous signals. They are appropriation of analog signal. The word digital stands for discrete values, and hence it means they use specific values to represent any information. In digital signal, only two values are used to represent something, that is 1 and 0 binary value. So binary signals are a special example of digital signals. So it is not necessary to always represent digital signal with 1 and 0. It can take any value on the y-axis. Now digital signals are less accurate than analog signals because they are the discrete samples of analog signal taken over some period of time. So digital signals are denoted by a square wave if they are represented as a binary signal. Digital signals are less accurate than analog signal because they are discrete samples of an analog signal taken over some period of time. Example, computer keyboard. Whenever key is pressed from the keyboard, the appropriate electrical signal is sent to the keyboard controller containing the ASCII value of that particular key. The electrical signal that is generated when key A is pressed carries information of digit 97 in the form of zeros and ones, which is the ASCII value of the character A. So if we are going to compare between analog and digital signal, so the analog signals are continuous in nature while digital signals are discontinuous, so they consist only set of samples. Analog signals are more accurate since they have an exact value at every point of time, while digital signals are less accurate because they are an approximation of analog signal. It needs an infinite memory while it can be easily stored as there is only less number of sample as compared to analog signals. In recording techniques, analog signal original signal is preserved, while in digital signals samples of the signals are taken and preserved. Examples of analog signals: human voice, thermometer, analog phones, though now they are digital thermometers also. And in digital signal examples are computer, digital phones, digital pens, etc. Now what is system? A system is defined by the type of input and output it deals with. Since we are dealing with the signals, our system would be a mathematical model or a piece of code or software or physical device or a black box whose input is a signal and it performs some processing on that signal, and the output is also a signal. So input is a signal and output is also a signal. The input is known as excitation and the output is known as the response of the system. In the above figure, a system has been shown whose input and output both are signal, but the input is analog signal and output is a digital signal which only defined at set of values. It means our system is actually a conversion system that converts analog signal to a digital signal, as you already studied about A to D converters. So conversion of analog to digital signals. How? There are two main concepts that involves in the conversion. First one is a sampling. Second one is known as quantization. Sampling, as its name suggests, can be defined as take samples. So sampling is done on the X variable. We can also say that the conversion of X axis infinite values in analog signal, there are infinite values on the x-axis, to a digital is done under sampling. So in case of digital signals, we have only a set of values on the x-axis. Sampling is further divided into upsampling and downsampling. If the range of values on x-axis are less, then we will increase the samples of values. This is known as upsampling, and it vice versa is known as downsampling. So there is one theorem known as Nyquist theorem that defines that how many samples we are needed to reconstruct a signal that is an close approximation of original signal. Now quantization. Quantization, as its name suggests, can be defined as dividing into quanta partition. Quantization is done on dependent variable. It is opposite to sampling. In that case, X is an independent variable while Y is a dependent variable. So quantization is performed on dependent variable. It means on Y-axis. So quantization is done on Y variable. It is done on the y-axis. The conversion of y-axis infinite values to 1, 0 and -1 or any other level is known as quantization. It is not necessary that you always quantize in the values of zeros, 1 and -1. It can take any values but only set of particular values. These are two basic steps that involved while converting an analog signal to digital signal. In our later on videos, we are going to discuss in detail quantization and sampling. So why do we need to convert an analog signal to a digital signal? The first and obvious reason is that digital image processing deals with digital images that are digital signals. So whenever image is captured, it is converted into digital format and then it is processed. The second and important reason is that in order to perform operations on an analog signal with a digital computer, you have to store that analog signal in the computer, which is not possible if we do not convert analog signal to a digital signal because analog signal needs an infinite memory. Now continuous system versus discrete system. Continuous system, this the type of system whose input and output both are continuous signal or analog signal is called continuous system. So this system is a continuous system where input is an analog signal and output is also an analog signal. While discrete system, the type of system whose input and output both are discrete signals or digital signals are called digital systems. So input signal and output is input signal is a discrete signal and output is also a discrete signal. Now this shows an electromagnetic spectrum. The electromagnetic spectrum according to the energy of photons is shown in this figure. In this electromagnetic spectrum we are only able to see the visible spectrum. So visible spectrum mainly includes 7 different colors Vibgyor that are commonly termed as Vibgyor. Our human eye can only see the visible portion in which we see all the objects, but a camera can see the other things that a naked eye is unable to see. For example, a camera can be used to see an X-ray, gamma rays or infrared. Hence the analysis of all that stuff is done in digital image processing. So why do we need to analyze all that other stuff in electromagnetic spectrum too? Because that other stuff such as X-ray has been widely used in the field of medical. The analysis of gamma ray is necessary because it is widely used in nuclear medicine and astronomical observation. Same goes with the rest of the things in electromagnetic spectrum. These are the various examples of digital imaging. So this one shows the natural landscape, then synthetic generated scene. This one is poster graphics, then there is a computer screenshot, black and white illustration, barcode, fingerprint, X-ray, microscopic slides, satellite imaging, radar image and astronomical data. So it has a numerous number of applications. So now I am going to define an imaging system. So this one is a source of energy, and when it illuminates the object reflects back, and these reflected lights are recorded by a sensor. As sensors are digitized, or sensor consists pixels, so images are digitized in digitized format, which is close approximation of original object. So this one is a real image, this one is a images that formed by the camera. So as there is a pixel, so this image is a close approximation of real image. The value pixel, the value of each sensor of the CCD array refers to the value of the individual pixel. The number of sensors is equal to number of pixel. It also means that each sensor could have only one value. So each pixel consists only one single value. Digital image common image formats includes one value per point per pixel. So that is black and white or grayscale image. 3 values per point per pixel is red, green and blue. 4 values per point per pixel is known as red, green, blue plus alpha. So you can clearly see in this figure, this one is a grayscale image. For example, if you are going to take an 8-bit, then the intensity will vary from 0 to 255. And this one is corresponding to red, green and blue. So there are the 3 images. One is corresponding to red, other is corresponding to green, and third one is corresponding to blue. And finally we are going to merge all these 3 images to get a RGB image. And similarly for the 4 values red, green, blue and alpha that consist of opacity. So we are going to start with grayscale images, and then later on we are going to extend into a color format. In the real world, objects are perceived by the eye because of light. So the sun, lamps and clouds are example of radiations. The object can be a people, industrial components, anatomical structure of a patient. The object can be a 2D or 3D or multi-dimensional mathematical model involving many variables. For example, a printed document is a 2D object, and most of the real world objects are 3D. So in the case of reflective mode of imaging, is the simplest form of imaging and uses a sensor to acquire the digital images. For example, all video cameras, digital cameras and scanners. So when the light is radiated by a light source, it illuminates the object and the object reflects the light, and this reflected light is recorded by a sensor, and this image sensor are able to convert light energy to a electrical energy. Now second one is emissive type of imaging. In emissive type of imaging, the radiation emitted by the object itself. So object itself radiated the energy, and that has been recorded by the sensor, and this sensor converts this light energy into a electrical signal. The example of this kind of emissive type of imaging is thermal imaging, magnetic resonance imaging and positron emission tomography. So in the case of thermal imaging, a special thermal camera is used in low light spectrum to produce images of an object based on temperature. Now the third one is a transmissive imaging. In transmissive imaging, absorption of radiation by the object depends upon the property of the material. So some amount of light has been absorbed by the material or an object, and some will pass it, and that has been recorded by sensor, which finally convert this energy into a electrical signal. So you can say in the case of X-ray imaging, or there are some kind of transmission mode microscopes, then an ultrasound imaging. These are the example of transmissive imaging. And scales of imaging can vary from a galaxy, that is an order of 10 to the power 28, to an electron microscope, that is an order of 10 to the power minus 6 meters. And its relationship with other field. So image processing consists low level processing. For example, image enhancement, noise removal, restoration, feature detection and compression. And image analysis consists segmentation, image registration and matching, while computer vision consists object detection, recognition, shape analysis, tracking and use of artificial intelligence, machine learning or deep learning. That comes under computer vision. But there is always overlap between computer vision and image processing. So what is an image processing? Algorithm that alter an input image to create a new image. So input is an image and output is also an image. So we are applying some kind of algorithm to get a processed image. For example, in this case, we are going to detect the edges. For that, we have applied some kind of filtering operations. So in that case, we are using a sober filter. So improves an image for human interpretation includes image display and printing, image enhancement, image restoration and image compression. So image acquisition is how do we acquire the images and How do I process and present the acquired image? In that we are going to study about filtering and image enhancement, image restoration, color image processing. Then how do we store and transfer image efficiently? Since image sizes might be a very large, which is very difficult, which might be difficult sometimes to transmit those images, since it needs a large bandwidth. So we have to compress those images. And finally, we recognize those images, object detection that comes under computer vision. So these are the key steps in digital image processing. So first we are going to acquire an image, then we are going to perform some kind of pre-processing, that is an image enhancement. Then we are going to segment the images, and then representation and descriptions, then recognition and interpretation, that gives you a final result. But all these steps involve the knowledge of the user. So now I'm going to explain the key steps in digital image processing, though in the later on chapter we are going to discuss in detail all these steps. So I will quickly go through this one. So first we are going to acquire an image. So in image acquisition, we are going to acquire the images with the help of cameras. So this one is the first process. So light is illuminated on the object and the reflected light is captured by the camera. Now, next point is image enhancement. Image enhancement is the process of manipulating an image so that the result is more suitable than the original for a specific application. As you can see in this figure, this image is a poor in contrast. So we are going to improve the quality of an input image by using some kind of operation. In this example, we are using a thresholding operation. So you can clearly see this image quality is better than the previous original image. The method is quite useful for enhancing an X-ray image, may not be best approach for enhancing the satellite images. Thus, there is no general theory of image enhancement. So the viewer is an ultimate judge who can decide that the final or processed image is better than the original image. Now, similarly, you can see in this figure there are a lot of salt and pepper noise that are available in this input image. So after using some kind of filtering operation, we are going to get a better image, or that output image has a better signal to noise ratio as compared to an input image. Similarly, this is a poor contrast image. So we are perform some kind of operation and finally we are going to get a better contrast image. The next step consists of image restoration. So image restoration is an area that deals with the appearance of an image. So there is a confusion between image enhancement and image restoration. But unlike image enhancement, which is subjective in nature, image restoration is objective in the sense that restoration techniques tend to be based on mathematical or probabilistic models of image degradation. For example, our input image is a blurred image, and this blurring because of the motion. So if we are moving in the x direction, then we are going to capture an image, might be image get blurred because our velocity or movement velocity is very fast. So if we develop some kind of mathematical model corresponding to that movement, and we are going to multiply the inverse of that model into an input image, then we are finally going to get a de-blurred image. So this technique is known as image restoration, in which we are going to restore the original image. Original image means the real image. Now, next one is a morphological, that deals with the tools for extracting image components that are useful in the representation and description of a shape. As you can see in this figure, there are a lot of noise that is present in this image. So we are going to perform some kind of processing techniques, and finally we are going to remove all these noise that are available here. So this comes under morphological processing technique. Now segmentation. Partition an image into its constituent parts or object. For example, if we have to find out that there is a tumor or not present in this area. So we are going to segment that area. So in segmentation, we are partition of an image into its constituent parts. That might be based on intensity or some other ways. We are going to group all those pixels that consist the same information. Now representation and description. After an image is segmented into regions, the result aggregate of segmented pixel is represented and described for further computing process. So representation and description is critical for successful detection and recognition of object in a scene. So to detect an object, finally we have to go for representation and description. Now, object recognition. Identifying objects in an image or videos is a key output of deep learning and machine learning algorithms. So we are finally identifying the object. Might be this one is a two-wheeler scooter. So this identification of an object is known as object recognition. Then there is image compression. So compression deals with the technique for reducing the storage required to save an image or a bandwidth required to transmit the image. So image compression is a familiar to most users of the computer in the form of image file extension. As you can see in this figure, there is a PNG format. So if we are going to store those images in the form of another file extension which is known as JPEG, so might be that will consume less space. So that is known as image compression. So there are various kind of techniques that are used for image compression. As you can see in this figure, that the original size of this figure is 1.2 MB. Then we applied some kind of image compression technique, and finally its size is going to be reduced up to 40 KB. So that will consume less memory. Now next one is a color image processing. That covers a number of fundamental concepts of color models and basic color processing in digital domain. Now the color is also used as the basis for extracting the feature of interest in an image. So they are also going to be used as one of the feature of an image for object classifications. Thank you.